Aloha BIOCHEM. In this lecture, we finish Chapter 4. We discuss resonance, isomers, and skeletal structures. So we'll finish a few remaining topics in the chapter. In the previous two videos, we hit most of the topics. And recall that the goal of this chapter is, if you're given a chemical formula, you need to be able to draw the Lewis structure, indicate its molecular shape, and also tell whether or not the molecule is polar. And of course, don't forget to name it. We saw many examples of that process in the previous two videos, so go check back on those if you need a refresher on how to do it. In this lecture, we'll touch on a couple of remaining and interesting topics, and we'll start with resonance. Resonance structures are two or more Lewis structures having the same atomic arrangement, but different electronic arrangement. Recall that when you draw the Lewis structure for a chemical formula, one of the first things that you do is to position the atoms next to each other. Now that's before you start connecting the bonds. So you have to get a certain atomic arrangement first. Now, what resonance is after you have an atomic arrangement, you will see often that there are multiple ways to connect the bonds. So you can end up with multiple electronic arrangements for a given atomic arrangement. Okay? And so you'll usually see this occurring in polyatomic ions. There's something about the extra charge associated with a polyatomic ion that causes resonance. Let's see how it works for the ion nitrate. Nitrate is NO3 minus. You remember polyatomic ions are like charged molecules, so you have a group of atoms that are attached together through covalent bonds, but there is an extra charge associated with it. So you might have like an extra electron or two, maybe, in the structure. To draw the Lewis structure for nitrate, we first write the dot structures for all of the atoms. So you have one nitrogen and then three oxygens. But don't forget that extra electron, which is indicated in the charge. So that -1 charge means we have one extra electron that needs to go into the structure. After you have the pieces of the puzzle, you arrange them how you think they'll fit together. And using symmetry as a guide, you have only one nitrogen, so put that one in the center and surround it with the oxygens. Now here is our atomic arrangement. Okay, but don't forget about that extra electron. To connect the atoms, we see that with these two unpaired electrons matched up and those two, we connect them to form the bonds. Okay, so there'll be a bond here, there, and there. But don't forget about that extra electron. That also needs to go into the structure, and we'll match it up with another unpaired electron. So it could go with this one or that one or that one. Let's just go ahead and put it on this one. So we're working our way towards the Lewis structure, and you know, we're getting there. So we'll pair this one up. There it is, and there are the three single bonds. And the whole structure now has a minus charge associated with it because of that extra electron that's in there. So we're not done yet though, and you can see that we're not by looking at the octets on the atoms. This nitrogen and that oxygen might have an octet, but these two only have 7. If you look at this oxygen, 2, 4, 6, 7 around it, and that one also has 7. So carbon, nitrogen, and oxygen always have octets. Now here, you need to get creative. When you're dealing with polyatomic ions with extra electrons like this involved, you need to get creative, and you'll see that oftentimes your common bonding patterns that you normally see are disrupted. And so nitrogen usually likes to have 3 single bonds, or maybe a double and a single, but 3 bonds. And I'll remind you what nitrogen looks like. Nitrogen, with its 5 valence electrons, 3 of them are unpaired. It likes to have 3 bonds. So there's a few ways that it can do that. The oxygen likes to have 2 bonds. Okay? But let's see what we end up with. So 3 bonds on the nitrogen, 2 bonds on the oxygen. Let's see what we have to do with nitrate though. Okay, so after we get to our, next step, we still need to get octets on everybody. Here's where we have to get creative. You can see already that the bonding pattern on this oxygen is disrupted. It only has 1 bond, okay? So common bonding patterns are going to be disrupted. Now here, we still need to pair up these 2 guys, and they're on different atoms. And so what we'll do is to simply split up this pair on the nitrogen. We'll take this one, pair it up with that, bring it all the way over to this oxygen. We'll put it there. And then take the other one, and we'll pair it up with this one through a double bond right there. And now we end up with this Lewis structure, which is a proper Lewis structure at this point. Okay, everybody has an octet. The common bonding patterns on the nitrogen and the 2 oxygens might be messed up. You see, nitrogen has 4 bonds here, and these 2 oxygens only have 1. So the common bonding patterns are disrupted, but there's nothing we could do to avoid it. So this is a good Lewis structure. Now, with this Lewis structure, before we ask about other resonance structures, let's first assign a 3-dimensional shape for the central atom. And to do that, remember, you count the number of groups around it. So nitrogen, I count 1, 2, 3 atoms, and I don't see any lone pairs. Okay, 3 atoms, 0 lone pairs. That's 3 groups total. So let's go to our, molecular shapes table, 4.2. So you go to 3 groups. So number of groups, 3. All 3 are atoms, 0 lone pairs. And this table tells us that the shape is trigonal planar. So that nitrogen will be in the middle and the oxygens are out there. And the oxygens all occupy similar positions. There's no difference between these. And so the bond angle you can see is 120 degrees when you have a trigonal planar geometry. Okay, so we will redraw this Lewis structure with its trigonal planar geometry right there. So the double bond's going down to the bottom oxygen, and the 2 single bonds are going up here and there. Now these oxygens are all occupying similar positions, and you might wonder at this point, what's special about that oxygen? Why does it get to have the double bond? Why can't the double bond have gone to one of those other 2 oxygens? Well, it can, and that's what yields additional resonance structures. Okay, so we can, with this atomic arrangement, which was modified from that to indicate the shape, with this atomic arrangement, we can indicate different electronic arrangements. So we can redraw the electrons on this atomic arrangement to yield multiple resonance structures. And the way we do that is to take this, a double bond and somehow shift it over there. And we can take 2 of these electrons from that double bond, put them back onto this oxygen, and then these 2 electrons from over there, bring them down to form a double bond. And now we have the second resonance structure, which you can see has an identical shape to the first one. This is also trigonal planar, 3 atoms, 0 lone pairs. And resonance structures must have identical shapes. Now, we can also have the double bond going to the 3rd oxygen, and so you can bring these 2 down here and bring those 2 back up there to get the 3rd resonance structure. So all three resonance structures simultaneously represent the nitrate ion. It's not the case that the structure takes turns looking like this and then looking like that and then looking like that. The double bond doesn't sometimes go to one oxygen and then sometimes go to the other one. What we would say is that all of the nitrogen-oxygen bonds have a little bit of double bond character to it. Okay, and it's just a limitation of Lewis structures. You can't just have one Lewis structure representing the nitrate ion. You know, there has to have three, and they're all three equivalent. One isn't more special than the other one in this case. So that's resonance right there. Two or more Lewis structures having the same atomic arrangement but different electronic arrangements. Now what about isomers? Structural isomers, we'll call them, are molecules with the same chemical formula but different atomic arrangements. So now we'll see that given a chemical formula, there can be more than one atomic arrangement. Okay, so atomic arrangements, you get atomic arrangements before you even start putting on the electrons and connecting the bonds, you know, to make double bonds and such. So that initial step of taking all of the pieces of a chemical formula and positioning them, there can be more than one way to do it. So we'll start with, as an example, this one, C2H6O, C2H6O. Now, if you're given this chemical formula and asked to draw the Lewis structure, it might be kind of challenging because you got a lot of atoms here. And so if you just start, you know, at the first step, you list out all the pieces of the puzzle. You got your 2 carbons, 6 hydrogens, 1 oxygen. How in the world are we going to connect these together? Well, we'll see that there are 2 ways to arrange the atoms. And so you're going to end up with 2 completely different structures. For the first one, we will take a look at the heavy atoms, you know, carbon, carbon, and oxygen. The hydrogens always go on the outside of a molecule. So just looking at the carbon, carbon, and oxygen, we'll put them as follows: carbon, carbon, oxygen. And we see that after the carbon and oxygen bonds are formed, where the 6 hydrogens go. You see this oxygen being bonded to this carbon now still has room for 1 hydrogen. And this carbon, while simultaneously bonding to the other 2, still has room for 2 hydrogens, and this carbon still has room for 3. So we see how the bonds are going to go now. Let's go ahead and connect them. So all of these turn into single bonds, and we end up with this structure right here. Okay? Now, if instead of putting carbon, carbon, oxygen, we had put carbon, oxygen, carbon, so now we have oxygen between the 2 carbons, and you know, we surround it with the hydrogens where they're supposed to go, we end up with that. These are 2 completely different molecules this time. Okay, the one on the left is actually a representation of ethanol. This is ethanol's Lewis structure, and the one on the right is dimethyl ether's Lewis structure. They may share the same chemical formula, but these 2 substances are completely different. For example, they have different boiling points. Ethanol boils at 78 degrees Celsius, and dimethyl ether boils at -24 degrees Celsius. And they have, all of their properties are different. They have different chemical properties. They do different things entirely. People like to drink ethanol, but no one likes to drink dimethyl ether. So completely different substances, just because they have the same formula doesn't really mean much. So we say that these are isomers. Now, when you draw a Lewis structure, don't get fooled into thinking there are more isomers. Suppose this Lewis structure had been drawn that way. Okay, is this a different isomer of that? Is this a different, are these different molecules? Well, no. If you take this molecule and you flip it over, you get that one. This is just a, you know, these are the same. if you can take one Lewis structure and deform it into another one without breaking and reconnecting bonds, then they're the same Lewis structure. Okay, even this one right here, look at this one right here, where it looks like that one, but now that you have that hydrogen coming down right there, even that is not any different. After all, this structure can be deformed into that one. You can just bend that hydrogen down there, and so this is the same as that. If you can deform one structure into another one, they're the same. And there's even another example of the same molecule. You take this structure right here, and you can deform it into that. You can bring this oxygen down in this position, bring that hydrogen up there. The oxygen and the hydrogen kind of slip past each other, but you don't have to break any bonds to turn this into that. And so even this structure is the same as that. Now you can see that all of these represent the same molecule if you just get rid of the hydrogen atoms. After all, they're just attached to the exterior. So get rid of the hydrogen atoms up here, leaving the heavier atoms, carbon, carbon, oxygen. And over here, you can see that would be carbon, carbon, oxygen. So, and maybe now you can see more clearly that these are the same. One would just be flipped over to get the other one. And then this one right here, is also carbon, carbon, oxygen. There's no difference between these, so hopefully it's more clear that these two are the same. And then this one right here would look like that, and you can see how this is easily deformed into that, and so these are also the same. In a moment or two, we're going to discuss skeletal structures, and if you look at the skeletal structures of this molecule and the other Lewis structures which represent it, you'll see that they're all the same skeletal structure. So skeletal structures, would help you see that these are all the same. So don't be fooled. This is the Lewis structure for ethanol, and that is too, and these are the same as this. Now looking at dimethyl ether, we can see that this is something completely different. Okay, there's no way to deform this structure and turn it into that one. You have to break bonds. Here you have oxygen connected to carbon and hydrogen, but over here it's connected to carbon and carbon. So you'd have to break bonds and reattach them in another way to get that. This is a different molecule entirely. Okay, and there are different ways that you can draw the Lewis structure for dimethyl ether. This one has the carbon, oxygen, carbon in a line, but we could have drawn it like that, but that would be no different. Okay, this can be deformed into that, and this would be the same as that. And the skeletal structures more clearly show you that they're the same thing. So that's isomers. Okay, resonance structures are all representing the same thing, okay? There's just different ways to draw the electrons on the same atomic arrangement. But isomers are where you actually do have different structures completely. Okay, different atomic arrangements completely now. They share the same chemical formula, but different structures completely. Now, skeletal structures are not mentioned in chapter 4 of your textbook, but I thought it's appropriate to discuss them at this point in the course. What these are shorthand representations of molecules' Lewis structures. So they're easy ways to draw Lewis structures. Some of the pros are they're very fast to draw them. And also, they will usually show some of the details of three-dimensional geometry as well. Now, when you have very large molecules, like the one we saw isn't really that large, but to draw the Lewis structure, it takes a little bit of time. Imagine if you have like twice as many atoms, or maybe 5 times as many atoms as that. Well, drawing the Lewis structure would take an extremely long amount of time, but its skeletal structure would be very quick. And you have all the information there when it's the skeletal structure. So when people draw Lewis structures for very large molecules, they'll usually just draw the skeletal structure. Let's look at an example. Here is another alcohol called N-butanol. Okay, so if you compare N-butanol with ethanol, CH3CH2OH, there's ethanol. Butanol is a larger alcohol. Okay, CH3CH2CH2CH2OH. Now here is the Lewis structure for N-butanol. Okay, you can verify that this is correct. All of the atoms are in their common bonding patterns. The hydrogens all have one bond, which is what they want to have. The carbons all have 4 bonds, which is one of their common bonding patterns. And the oxygen has 2 bonds and 2 lone pairs, which is what oxygen does. So this is correct. Now, before we get to the skeletal structure, let's just convert this to its 3-dimensional structure. So remember, all of these carbons are tetrahedral because they all have 4 atoms they're connected to. 2, 3, 4, and 0 lone pairs. So all of the carbons are tetrahedral. All right, 4 groups, all 4 atoms, 0 lone pairs, they're all tetrahedral. So you can see how to draw a tetrahedron on paper. So applying this method, all of the carbons are going to look kind of like that. So you have, hydrogen, carbon, 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 and then the oxygen is bent. You have 2 atoms and 2 lone pairs. That's the bent situation over here. And the wedges are coming out of the paper, okay? The wedges are coming out of the paper. The dashes are going back into the paper. So maybe this is a little bit more accurate than that one. Okay, so let's take this and let's convert it into its skeletal structure. Doing this is very simple. The first thing we do is get rid of any hydrogens that are attached to carbon. Not all of the hydrogens, only the one attached to carbon. So remove hydrogens attached to carbon, and then this turns into that. You keep that one attached to the oxygen. And then the next step is to remove the carbon atoms. Okay? So instead of this, you just make it look like that. And so here there is a carbon there, and there. That's where the 4 carbons are. We don't need to draw them. We know that there's one here at the end of this line. We know there's one there, there, and there. Okay, so we're almost there. The last step is to clean it up. Instead of having a line between O and H, we just simply write OH, and we get rid of the lone pairs. So we just clean it up. And this is the skeletal structure for N-butanol. Now, if you have a skeletal structure, you can always convert it back into a Lewis structure. And you do the exact opposite. Okay, using any non-carbon atoms like this, you know that this oxygen, if it's bonded to, that must be a carbon there, if it's bonded to a carbon and a hydrogen, then there's going to be 2 bonds on this oxygen. It must get 2 lone pairs. Oxygen looks like this. It's either a double bond and 2 lone pairs or 2 single bonds and 2 lone pairs. And it's going to be this form. The oxygen has, you have 1 atom over here, and then there's another atom over there. This is going to be 2 single bonds and 2 lone pairs. Now, we know that there are always carbons at any vertex or any end of the line. So that's a carbon too. So whenever you see a skeletal structure, you can see immediately where the carbons are. They're at any end of the line or any vertex. And so let's just draw them in. So now we put the carbons in. Then the last step is to fill in the hydrogens. And we can do that easily because we know that carbon always has 4 bonds. Okay? And if you see 2 bonds on a carbon, then you know that the other 2 that are not drawn are where the hydrogens are. So this carbon already has 2 bonds. It must get 2 hydrogens. This carbon has 2 bonds, so it must get 2 hydrogens. This one has 2 bonds already, so it also gets 2 hydrogens. But the last one only has 1 bond, so 3 hydrogens go here. And so you should be able to turn a Lewis structure into a skeletal structure and back. Let's do this again. The next example is benzoic acid. The chemical formula is C7H6O2. You'd be pressed to draw the Lewis structure for that. There would probably be many isomers of this one. Many atoms usually yield many isomers, but if I told you the formula like this, C6H5COOH, you might be able to get it with some experience, but here it is. I'm just going to give you the Lewis structure. So this is a molecule of benzoic acid, okay? And let's draw its skeletal structure. So again, any hydrogens attached to carbon, that's these 5, we get rid of those. Okay, now get rid of the carbons themselves. And we cleaned it up in the same step. So we got rid of the lone pairs on the oxygen, we got rid of the lone pairs on this oxygen, and then also that bond, and so we shortened it to that. So there you go, that's the skeletal structure for benzoic acid. And looking at any part of this molecule, you can see what's there. You remember, carbon is always at a vertex or the end of a line. So this carbon right here, since it already has 1, 2, 3 bonds, the fourth one must be the hydrogen. So this one gets 1 hydrogen. And what about that carbon right there? It already has 1, 2, 3, 4 bonds, so no room for any hydrogens there. This one also has 4 bonds, so no hydrogens on this one, but this one gets a hydrogen, that one gets one, that one gets one, that one gets one, and that one gets one. Okay, so that's benzoic acid. Here's another one. This time we'll go backwards. We'll start with a skeletal structure, and this is for alanine, one of the amino acids that make up protein. So here is the skeletal structure for alanine. You have H2N, and then a vertex here. This is the end of a line, and then another vertex. Here's an oxygen, and here's an OH. Now, what we'll do is we'll put the carbons where we know the carbons are. The carbons are at the vertexes or the end of the line. So here's a carbon there, there, and there. And we'll also put a bond between the oxygen and its hydrogen, and also between these 2 hydrogens and that nitrogen. And so there you go. We're getting there. Now, we know that oxygen always has 2 bonds and 2 lone pairs. 2 bonds and 2 lone pairs. I'll remind you what oxygen looks like. Okay, it's either 2 single bonds and 2 lone pairs, or a double bond and 2 lone pairs. All right, and so here's a double bond, so it gets 2 lone pairs, and then here's 2 single bonds, so it gets 2 lone pairs. And then carbon always has 4 bonds, so I see 4 bonds on this carbon, so no hydrogens go there, but this one I only see 3 bonds, so there's going to be a hydrogen that goes here. This carbon only has 1 bond, so it must get 3 hydrogens. And what about the nitrogen? Remember, nitrogen always has 3 bonds and 1 lone pair. 1, 2, 3 bonds and 1 lone pair. So you see it's missing its lone pair. And then the last step would be to simply put the hydrogens, there they are. And that's alanine. And you can see the formula is C3. How many hydrogens? 1, 2, 3, 4, 5, 6, 7. H7O2. C3H7O2. Oh yeah, N. Forgot the nitrogen. So that's skeletal structures, and I'll maybe show you one more that we saw at the very beginning of our chapter. We looked at acetaminophen. Acetaminophen has the following Lewis structure right here. Okay, this is the active drug ingredient in Tylenol. Now here is its chemical formula, C8H9NO2. Okay, this is the proper Lewis structure, and you can see that all of these atoms are in their common bonding patterns. Oxygens have 2 bonds. All of the carbons have 4 bonds. The hydrogens all have 1 bond. The nitrogen has 3 bonds and a lone pair, and so this is correct. Okay, and you can even see its ball and stick model and look at some of the geometry inside the molecule. But what about its skeletal structure? Okay, what about its skeletal structure? There we go, you can see it a little bit better. Well, skeletal structure, let me see if I can pull that up for you. Sorry, I have to find it briefly. Give me a moment. Can you imagine what its skeletal structure looks like? Here we go. Okay, so you see, if you take this right here, you get rid of any hydrogens attached to carbon. Okay, so over here, that's going to be this carbon. And then you get rid of the carbons. So you got basically a hexagon with, double, alternating double and single bonds right there. And then this will be the oxygen, get rid of the lone pairs, and there you go. So that's a skeletal structure for acetaminophen. That does it for chapter 4. In our next chapter, we will get to chemical reactions. So stay tuned for that. Aloha.